All right, let's take a look at the volume of prisms and cylinders. So yesterday we kind of focused on surface area, which is the area of a three-dimensional object, right? It's the area of all the faces. And today we're going to look at the volume. So volume is another three-dimensional thing. It's the three-dimensional space. So area is the space inside a 2D object. Volume is the space inside a 3D object. So let's just kind of look at, let's draw something not too complicated, and it's not going to be perfect, but okay. So that's a 2D rectangle. It's a rectangle, which of course is 2D, and it's 2 by 3, and it has an area of 6. But really, let's envision it that these are 1 deep. And so really what we're looking at is the front of a rectangular prism. And so the front is what you're looking at is you see 6 cubes. Okay, and then let's extend that maybe 3 deep. Okay, so let's give it some depth. Okay. And so I know I didn't do this perfect, but something. Something like that. Okay, so what we really now have is a rectangular prism, and hopefully you can kind of see all the cubes. So there are 6 cubes in this front, 6 cubes in the middle, and then there's 6 cubes on the back. So we know there are 18 cubes, and let's say they're all 1 inch by 1 inch, which is to say that we have a volume of 18 cubic inches. Okay, I know this is review. There's no way we've made it this far in math without talking about the volume of a prism. So a rectangular prism, most people would say that the volume is just length times width times height, right? You're looking at all 3 dimensions. The length and the width give you the number of cubes in that front face, and then you really are just multiplying by the height. What I really want to emphasize is that idea, because that's going to be the common theme that we have for prisms and cylinders, and really it's a ton of calculus. And I know you're not going to be in calculus for a long time, but the idea of like stacking a 2-dimensional shape to then build a 3-dimensional shape is super important. Again, what you're doing is, again, you don't have to actually draw these cubes. You can take any rectangular prism you want, draw it back, right? Something like that. And what we're really saying is the volume of this rectangular prism is really just stacking all of these shapes. We can make them infinitely small we want. So you take these really thin things and you stack them, right? You take a 2D area and then you stack a certain number of them. So maybe the height or the depth. Some people are going to call it the depth if it goes this way, the height if it goes this way. We'll call it the height here. And so then really the volume of any prism or in fact cylinder is really the area of that base times the height. Now in the traditional formula, right, clearly the length times the width gives us the area of this front face, right? So we take the area of that front face, which is 6, right, 2 times 3, and then multiply by 3, and we get the same thing. This is just the more generalized version of how to find the area of a prism or a cylinder. Now, think about a cylinder, okay? Now, if you looked it up in a book or you remember, so here's your cylinder, okay? And you know, if you looked it up in a book, the volume of a cylinder is going to be pi r squared h. Okay, that's going to be the volume. But what I really want to emphasize is that it's really a cylinder is stacking a whole bunch of circles. So if you think of a cylinder and we stack a whole bunch of quarters, right? If you knew the area of this, A, That's just this guy, pi r squared, and then you multiplied by the height, meaning the number of quarters you stacked, then you actually get the volume. The same thing. This is also true for both of these things. These are the traditional formulas, right? For a rectangular prism, length times width times height. For a cylinder, pi r squared h. But really, it's just the area of the front face, or the top, multiplied by how many you are, and that is a huge principle in calculus. It's actually like the entire semester of Calc 2, the idea of building volumes by stacking things. Here we're stacking a rectangle, and here we're stacking a bunch of circles. The point of all of this is it extends beyond just these two. If it was just these two, well, then we probably wouldn't ever look at this. But the idea here is that we can actually go beyond cylinders. We can do anything then. So I can take a hexagon. Bear with me on this. I'll do my best to draw it and not totally mess it up. Can you see all of that on that paper? Okay, so I'm going to connect these, of course. Something that looks like that. Okay, so the idea is, what's the volume of a hexagonal prism? Well, it's the same thing. The volume is just the area of the base times the height. Now, when I say the area of the base, I'm talking about this front face here. It's not actually sitting on it the way I drew it. So the area of this hexagon, and we know how to do hexagons and octagons based on our last test, right? We spent a whole unit finding the area of this, and actually we spent yesterday doing the surface area of a shape like this, in which you had to find the area. So if you think about this, what you have here is you're stacking hexagons. Now, I can't really draw all of them, right? But if you kind of looked at a side view of that, you can see that this hexagonal prism is just a hexagon and then stacking a bunch of them, right? The front is a certain area, and then you add height to it, and then you give it depth. And so if you said, oh, this front here is 10 square inches, right? And then this was 12 inches deep. It's kind of like thinking you have 10 cubes here and you have 12 of them stacked in a row. And so then the volume is then just going to be this area times the height, and you're going to get 120 cubic inches. And again, I'm not saying this can fit perfectly, like cubes wouldn't fit in there, but it's the same area as 10 squares, and then you're adding 12 of them deep. Again, the huge principle here is whether it's a hexagonal prism or a rectangular prism or a cylinder, all of these things follow this same formula. The volume of it is the area of the front face or the base times the height or the depth, and it can kind of depends on how you are viewing these things. Again, this, I probably would say this was like a depth, but in a cylinder here, the way I have this stacked, I would say this is a height. Okay, so we can do rectangular prisms, we can do triangular prisms, we can do hexagonal prisms, and we can do cylinders. The volume of these guys are all the same thing. Lots of times, it's just kind of easy mathematically to do these aren't hard calculations. It's just a lot of just kind of plugging and chugging in, right? I mean, if I give you a cylinder and I give you the radius is 5 feet, and I say this is 8 feet, right? This is like some industrial tank holding, oil or something, and I want to know the volume of this thing. The volume is just the area times the height, or just pi r squared h. And so we're just kind of plugging this in. Pi, 5 squared times 8. 5 squared is 25. 25 times 8 is 200. And so we get 200 pi. And that would be cubic feet, right? 200 pi is like 600 and something. Like 628 or something. cubic feet. Lots of times with cylinders, just like we did with surface area, we leave it in terms of pi because it's just exact. Where like a rectangular prism or a hexagonal prism, we're actually going to go ahead and find the numbers. Just like yesterday, I could ask you for things in reverse, right? I could give you some. I could give you some rectangular prism, and I could say, oh, this is 5. This is 6, and I don't know what this is. This is just some height, but I know the volume of this thing is 600 cubic meters, right? But you know that the volume of these guys, either the area times the height, right, this front area, or the more traditional way for one of these guys is just length times width times height. And then we just kind of plug in. This is just 600 equals 5 times 6 times what, right? So then this is 600 and this is 30, divide by 30, and you go, oh, you get a height of 30 meters. Makes sense? So I certainly could give you the volume and you could find certain dimensions. I could clearly give you the dimensions and you can find the volume. Okay, hopefully this gets you started on finding the volume of cylinders and prisms and reminds you of this huge concept that this is really what, an upper level type idea of a stacking principle, that the volume, we can take the cross-sectional area of something and we can multiply by the depth to get the volume. Okay?